Good evening, everyone. Welcome to the 18th interactive session in GATE NPTEL series. So let us continue with soil mechanics. We also have some problems to solve from the last session and this session. So let me continue wherever we left last time. So we were looking at the idea of flow through collapse. So we were looking at what are the ways in which water can interact with soil, and we saw different types of problems arise. And then we derived the continuity equation, which is essentially the conservation of mass. And then we looked at Darcy's law, which relates the discharge velocity to the hydraulic gradient. Yeah, that is this. And then we derived the governing equation for seepage. So this is Darcy's equation. And then this is the continuity equation in general. And then we finally derived the Laplace equation. So when we have an isotropic soil, that is Kx equal to Kz, we saw that the governing equation for the total head is the Laplace equation, del square h by del x square plus del square h by del z square equal to 0. And then we looked at the types, how do we solve this? So in general, if we have a function psi such that these relations are satisfied, and for your information, these are known as the Cauchy-Riemann equations. So that comes from a different point of view. So in complex analysis, this function psi and h are the real and imaginary parts of an analytic function. So if they are such that these two are conjugate, then these relations are satisfied. And it turns out that this conjugate harmonic function of the total head h corresponds to the velocity, the flow lines. So the tangent to the conjugate harmonic function gives the velocity vector at a given point, and h is equal to constant describes a equipotential line. So this is what we saw. So given a dam like this, if we have say there's a sheet pile or something which is separating two different levels of water, and the soil beneath that is permeable. So water will automatically go from this side to this side. And a solution is usually obtained graphically in engineering analysis. And we saw if there are n drops in, so we saw these lines correspond to equipotential lines. H equal to constant correspond to equipotential lines, and psi equal to constant will correspond to flow lines. So, and we also defined what is a flow channel. The space between two flow lines, we call it a flow channel, and that carries some amount of flow. So it's like a series of pipes connecting this side to this side, and the space between two it is some kind of discretization. So the region, so psi equal to constant corresponds to one flow line. So the space in the space between two such flow lines, we can assume the velocity field to be constant. So this velocity is calculated using the Darcy's law, and then given the velocity and the spacing between the two, we also get the flow in this channel. Then multiply this by the number of flow channels, we get the total seepage. So that is called the seepage loss. And when we have certain approximations that this flow field, which is obtained by the intersection of two flow lines and two equipotential lines, if these the network is called a flow net, and one element of it is called a flow field, and if each element is approximately square, we have the simplified formula for estimating the seepage loss from a dam or any water retaining structure. So this is where we stop, and there are other problems that we need to look at. So this problem we solved last time. And then we saw if the soil is anisotropic, we don't get the Laplace equation. So we need to do a certain transformation to the independent variables. So x and z are the independent variables. If we do certain transformation, we can transform this equation to the Laplacian. So we choose the scaling factor r such that we get the Laplace equation. And that gives this other concept. So if you multiply the horizontal coordinate by this factor square root of kz by kx, we get the Laplace equation, and then we can construct the flow net in the transform geometry. And we also solve this problem of seepage between two wells. Let's look at the other ideas today. So other than that, any doubts? If you have any doubts, we can take up. I think there's no question in the forum. So if you have any doubts, you can tell me now. Otherwise, I can proceed. Okay. So there are certain. Let us see how do we measure permeability. So there are some. Let us see what is the range of permeability. Typically, the permeability or the hydraulic conductivity K is the hydraulic conductivity or the permeability of the soil varies greatly. So if you take, I hope I'm audible, right? Yeah.
Yes, sir.
Okay. Okay. So if you take something like if you take something like coarse gravel, the permeability of the order of 0.1 centimeter per second, right? So this comes under very permeable. And if you take something like sand, so you know sand is also granular soil, and there the permeability varies between 10 power minus 3 to 10 power minus 1 centimeters per second. Similarly, if you take silty sand, and there are other cases, but let me. If you just take pure clay, it has a permeability of something less than 10 power minus 7 centimeters per second. So this is the usual range of permeability of soils. So again, silt comes somewhere here. So silt is about 10 power minus 7 to 10 power minus 5 centimeters per second. So this is the usual range. Now, how do we measure this? So one is there is an empirical relation. It's called the Hazen's relation. As you can see with so what is different between all this? It is the grain size. So the coarse gravel has a larger number of large size particle, whereas clay has a large number of very fine sized particles. So the permeability can be directly related to the grain size. If you have to, permeability depends on how much area is available for water to flow through. If the grains are larger, the interstitial spaces are also larger. Therefore, Hazen gave this empirical relation between the permeability um, and the grain size. So that is K is equal to C D10 square. So there's an empirical relation. So the units are important. K is measured in centimeters per second. Uh, D10 is measured in mm. So what is D10? So D10 is nothing but if you draw the grain size distribution of the soil. So you have grain size on or sieve size, whatever. You have the sieve size here, and you have the percentage mass, which is which is less than or equal to that size. So as the grain size increases, you see more and more number of uh, there is more soil will fall into that place. So typically you have a distribution like this, which is sigmoidal. Now corresponding to 10%. So what is the size? What is the size of the particles that is not exceeded by 10% of the soils? If you see that, that comes around here, and this value is nothing but D10. So you do the usual sieve analysis. You put a series of sieves, take the soil from the top to till the bottom, and then find out what. So the soil retained on every sieve gives the percentage of the percentage by mass, which is greater than or equal to that sieve size. So if you take a point here, it means that this amount of soil was retained on the sieve size greater than or equal to this. Similarly, this 10%, this D10 is the diameter or the grain size, which is not exceeded by 10% of the soil. That's all. And C is usually between 0.4 to 10. So it varies between 0.4 to 10. It has got weird units, as you see. It's an empirical relation, so it will have some weird units of, say, centimeters per mm square per second. And at an average, you can take the value to be 1. So this is one way. It is just an empirical relation. We do a sieve size analysis of the soil and then use this empirical relation to estimate the permeability. This is one way. However, this does not take into account the effect of pressure, right? Suppose you have a soil, in field, and it is kind of in the vertical direction, the soil is always subjected to some pressure due to the loading. And the horizontal direction is relatively free. So this can be anisotropic. And the soil structure has certain properties. So directly relating to this doesn't make sense, because sometimes you can have a closer packed. So if the soil is under stress, we know the grains are packed closer to each other. So this has certain limitations. So we have two laboratory tests. So laboratory tests to measure the permeability are, one is the constant head permeability test, and the other is the falling head. So it is very simple. In constant head, what do? We directly make use of the Darcy's law. So we construct some setup like this. Maintain this water level here with a constant inflow Q. And then somewhere here we put the soil. And this is the tail. So here you have some head, here you have some other head, and here whatever goes in has to come out. So the same flow rate is maintained. So when this Q is kept constant in time, and we assume the soil is fully saturated, this head is also constant. So let this head be delta H. And the soil is packed inside this. So on to avoid the water carrying away the soil, on the top side and the bottom side, they put a pervious, something like a sandstone, which is pervious, and it gives mechanical stability to the soil which is inside, but it does not affect the permeability. So if you take it as here, we have the soil, and the length of flow through the soil is L. Just take this as L, and the cross section to be A. So directly you can apply the Darcy's law. So you assume that these pipes are frictionless. There is no frictional dissipation. There is no head loss across the pipes. There is no head loss because this thin layer of gravel or sand, that is not going to affect the head too much. Same on this side, it only gives mechanical strength to the soil inside. So directly you can apply the Darcy's law. So what is the discharge velocity? It is Q by A. But by Darcy's law, it's also equal to K I. But what is I? I is the hydraulic gradient. What is the head difference between this point and this point? So we assume the pipes are all frictionless. So the head here is equal to the head here. Similarly, the head here is equal to the head here. So the head difference is nothing but delta H. It is nothing but K delta H by the length along the flow. It is delta H by L. Now equate the two. Q is what we are maintaining. Area of cross section is determined by the geometry. Therefore, the permeability K is nothing but QL by A delta H. That's all. And how do we measure Q? So Q is the discharge flow rate. So if we, it is usually measured as you have a container here, say a measuring jar, put a measuring jar here, and you wait for some time t, and it will collect an amount V of t. So Q is usually the volume by time. So in that case, you can write the constant head permeability as, you can write it as, it is just VL by A delta H T, where T is the time of observation, V is the total volume collected in that time of observation, L is the length along the flow, A is the cross section of the soil sample, and delta H is the head difference. Now the problem here is if we have very impervious soil here, say if we have clay or something, the time you need to collect a measurable amount of water will be very high. So as I said, clay has a permeability of something around 10 power minus 7 centimeters per second. If you substitute the values, you see that the time required will be in some days. And that will delay a lot of things. So instead of looking at the time taken to collect a fixed amount of water, they allow the flow rate to vary. So that is the other case, which is called the falling head permeability test. So in the falling head permeability, uh, the time is fixed, the time of observation is fixed, and then you allow the water level to drop from, say, so in the beginning of the test, suppose the head is here, and by the end of the test, suppose the head is here. So this is T is equal to T1, this is T equal to T2. And then again, the rest of the setup is the same. It is connected to a soil sample. And there is a tailwater level. There's a here it is maintained here. So this is allowed to vary, but here it is maintained constant. And then again, water flows into some measuring jar. Or actually, you don't need a measuring jar because we are allowing it's not anyway constant. So water just flows out. And as in this case, the soil is packed between two pervious stones. So you have soil here. Now let us take suppose this is taken as the datum. Suppose this is taken as the datum. The initial head is, so this is the final head, and this is the initial head. So the initial head is delta H1, the final head is delta H2. So flow rate is not maintained a constant, head is not maintained a constant, but we are just measuring how much the head changes in a given time. So we are measuring over a given time. Now, how do we find the permeability? Just use the Darcy's law again. So the flow again, you can take the discharge velocity, but now it is a function of time. So the discharge velocity at any time is Q by A. A is constant, so no problem. But Q is a function of time. So this is the discharge velocity as a function of time. Q is a function of time. And then so what is Q equal to at any given time? It is, let us say this has a cross section A, small a, and this has a cross section capital A. The soil has a cross section of capital A, and the water has a cross section of this tank, which is maintained above that, has a cross section of A. So the volume of water in the tank above. So this is the decrease in the water level. So let us call the total decrease as some. So let us assume the volume of water here is V of t, V at any time t. So the volume at any time is equal to the area of cross section multiplied by again, let us take the base to be at some h naught, right? So the volume, if you consider a cylinder or whatever prismatic thing, it is just A into delta H of time t minus h naught. So it is nothing but A into the head difference minus H naught. Now, what is dV by dt? The rate at which the volume changes is nothing but A is constant. This varies. This becomes d by dt of the head difference. H naught is a constant. That is a part of the experimental setup. But what is the rate of change of water? That is the flow rate. So the rate of decrease of water here. At what rate the water decreases here? That is equal to the flow out of the tank. So that is nothing but dV by dt is nothing but minus Q. Because this delta H is decreasing, this will be a negative quantity, but flow rate is always positive. So we have a minus Q of T. Now just put that back here. So the velocity here is nothing but minus A by capital A d by dt of delta H of T. But what is the velocity also equal to? It is equal to, so this velocity as a function of time. By Darcy's law, it is equal to K times the hydraulic gradient. What is the hydraulic gradient? Here it is the head loss by the length of the flow. Again, the length of the flow is constant L. So this is equal to minus A by capital A d delta H by dt. Now, what is the only unknown in this equation? These are geometric parameters. Those are fixed. K is what we need to find out, and that is fixed for a given soil. So H of T is the dependent variable, and T is the independent variable. So this is an ordinary differential equation. So just you can do variable separable. So you get d delta H by delta H is equal to K A by AL. So there's a minus sign. No, fine. This is fine. So this is fine. So this is equal to Ka by small al dt. And integrate on both sides. So this goes from T1 to T2. And this goes from at time T1, what is delta H? It is delta H1. And this is delta H2. So on the left hand side, you have a natural log. So this, let me put ln. So this is 1 by integral 1 by x. This is natural log of delta H2 by delta H1 is equal to minus Ka T2 minus T1 divided by AL. Now rearrange. So H2 is less than H. The head loss finally is less than head loss initial. So this is a negative quantity. This negative multiplies with it. So you finally get the permeability as the hydraulic conductivity or the permeability as AL by capital A T2 minus T1, which is the time into log of delta H1 by delta H2. So when you do a falling head permeability test, so this is when you do a falling head permeability test, K is determined according to this equation. That's all. Now, there are also cases where you can you have aquifers, and this topic is also there in hydrology as a part of hydrology in GATE syllabus. So you can also look at this right now. This comes under well hydraulics, steady state well hydraulics, but it's also a topic under permeability. Now, there are two cases again. So this part is fine. I guess this part is fine. We can look at this aquifers. So aquifers is a region of pervious soil stratum which contains water, right? If it is impervious, it doesn't allow the percolation of water. If it is pervious, it can hold water in the voids. So when we have a pervious stratum sandwiched between two impervious stratum, we call it an aquiclude. And when we just have a pervious stratum with a free groundwater surface, it is an aquifer. Now, again, these equations are derived directly by using the Darcy's law and the 1D flow equation. So here, first let us consider this case of a confined aquifer. So you have, there is there's an impervious soil here, impervious subsoils mass here, and the bedrock, this can be the bedrock or another impervious soil, and the pervious stratum is confined in between the two. So when the soil is confined here, there can be this the water here can be pressurized because it is not free to flow into the impervious stratum. So it doesn't have a free surface. So when we dig a well into such a soil profile, the water will rise to a certain extent. Now, in this case, if you say, let us take the datum of the total energy line as here. Let us take this as H equal to 0 line, the total head to be 0 at this line. And when we drill a borehole up to the bedrock, the water will rise up to some level. So a borehole, a well or a borehole acts as a piezometer in this case, right? So when you have flow through some pipe, you connect a thin tube to the side. What it measures, it just measures the pressure level. So water will rise to a level H, which is nothing but the pressure divided by the unit weight of water. If you apply Bernoulli's theorem, you know that is a piezometer. When we have water, groundwater, and you drill a borehole, that acts as a piezometer. So the level to which water rises is nothing but the total head of water at that point. That you can easily verify by using the Bernoulli's equation between the water surface and the point there. So suppose we'll drill a well here, and we are pumping water out at a constant flow rate of Q. And somewhere away from the well, you drill another observation hole. And when we drill a hole, immediately water rises because it has to equilibrate with the atmospheric pressure. So there is water surface at some pressure, but that cannot be in equilibrium. So if you take the water interface, this will be at some pressure. But when it is exposed to the atmosphere, the pressure on either side should be equal to the atmospheric pressure. So the water will rise to some height. What is that height? That height is the total head. That is the elevation head plus the pressure head. The velocity head, as I said, is very small when we consider soil mechanics problems. So that is the total head. Now let us consider the, you can just use the equation of, you can use Darcy's law between this. Now, water is flowing into this, when we pump water out of a borehole or a well, water is flowing into that well from all directions. Now, if you see the plan, you have a borehole here and water is flowing from all directions. Therefore, and let small h be the head at any point, the head to which it rises, and let R1 and R2 be two observation wells, right? So let us take R1 and R2 to be two observation wells. Now in that case, again, you start with the Darcy's law. So V is nothing but K times the hydraulic gradient. What is that? LH by dr. We are assuming the situation is axisymmetric. You have one point you're pumping, and from all directions water comes in equally. So this is the discharge velocity. It is dH by dr. But what is V? V is nothing but you're maintaining a constant flow rate. V is nothing but Q by A is equal to K dH by here, and you have a minus sign because it relates to the loss of head. So with increasing R, H increases, and the flow is towards the inside direction. So you have a minus sign. Now you take a circle at a distance of R from the well. Suppose this distance is R. What is the area of flow at this distance? What is the area this Q is coming? So at every point, let me use a different color. So you consider a radial circle. You consider at a radial distance R, you can consider a circle, and we are assuming that the flow into this well is equal from all directions. So at every point, you have a discharge velocity of V. What is the flow Q? It is nothing but V into area. What is the area? It is 2 pi R times this thickness of the pervious layer, capital H. So this is nothing but Q by, what is the area of the flow? It is 2 pi R into thickness of the pervious layer, capital H. And this is equal to minus K dH by dr. So what is constant? This is constant. This is constant. R is not constant because you're having two different, your H is a function of R. So this is a dependent variable. This is a constant for a confined aquifer. Rearrange. So uh, we get Q by 2 pi H into, let us have it, dr by R is equal to minus K dH. Now integrate on both sides. So when R equal to R1, H is equal to H1. And when R equal to R2, H equal to H2. If you do this, you get Q by 2 pi H natural log of R2 by R1 is equal to K into H1 minus H2. So again, so what we want to find out, so either you use, so we have got this. This is basically this. So you get 2 pi H K into H1 minus H2 divided by log of R1 minus R2. So where H1, H2 are the levels, if you measure this directly at R1 and R2 respectively, where R1 is closer and R2 is farther away. Right. Similarly, for an unconfined aquifer, so this is for a confined aquifer. So let me check once. So this is so the head is decreasing towards the flow, towards the center. And then R1 is, R2 is greater than R1 and H2 is greater than H1. So right, so the velocity you have, so this, here you have another minus. So this velocity is radially inwards, but we have taken R positive radially outwards. So R is radially positive radially outwards, but velocity is actually inwards. Q is taken out of the well, and if you're pumping inside, the case is different, but you're pumping out of the well. So this velocity V is actually along the negative R direction. So you have a minus here, which means you have a minus here. So this will also be just, you can write it as H2 minus H1. You have a minus sign, overall minus sign multiplied, that's all. So that doesn't, that's basically a convention issue. So you just, H2 minus H1 and R2 minus R1 are in the same. So H1 is greater than H2. So this is negative, this is negative. So all other quantities are positive. You can just make a simple check. On the other hand, if you have a confined aquifer, unconfined aquifer, so this is, if you have an unconfined aquifer, you have a well, as in that case, we have a well, and you have observatory holes. As in the previous case, so we are pumping water out of this well at a constant flow rate Q. So therefore, compared to the natural water table, so the natural water table may be here. Compared to the natural water table, the water will be drawn down. Therefore, it comes like this. So water is being pumped out, which means if you see the plan, this is the borehole, and at a distance r, water is flowing towards the borehole from all directions, towards the well from all directions. Therefore, since the water is flowing towards the well, there has to be a head loss in this direction because it is flowing through soils. It has to do work to flow through soils. So as per the Bernoulli equation, there is head loss as it flows. Now again use the, now here what is the total, here when you do a borehole, the water is not going to rise because this has a free surface. The entire stratum is pervious. So at this point, at this free surface, the pressure in the water is equal to the atmospheric pressure. Therefore, when we make a borehole, when we make a well, it directly, water surface is exactly where the free surface is, right? It doesn't rise above the free surface. So let this height be h1 and let this height be h2. Again, we have the usual Darcy's equation. So the velocity is equal to k into the hydraulic gradient, and in this case, the hydraulic gradient is partial h with respect to r. Now, as I said again, we should be careful. So there's a minus sign in the usual Darcy's equation, and this velocity is inverse. So this is minus of q by a. It is minus k partial h by partial r. Now, what is the area of the flow? Area of the flow is 2 pi r h, where h is also a function of r. That is the only difference. Rest is all the same. You cannot treat h as a constant in this case. The rest is all the same. So we get q by 2 pi r h is equal to k dh by dr. Now rearrange. We get q by 2 pi integral dr by r. When r equal to r1, we have a k h dh. When r equal to r1, h equal to h1, r equal to r2, h equal to h2. Just integrate directly. What do we get? So we get, let me write down the final expression. So the final expression, if you see, this will become h square by 2, which is h2 square minus h1 square by 2. Therefore, we have q by 2 pi into h2 square minus h by 2. So this 2 gets cancelled. h2 square minus h1 square into the natural log of r2 by r1. This is equal to the permeability. So these two are, that's all. That is exactly the equation we have here. Pi with some rearrangement. You have a pi by h1 square minus h2 square here and ln r2. So these two are two important equations. So here capital R is taken at a large distance r, and r naught is taken at the level of this bore well. You don't need two observations. That's all. So these are two important equations that often arise in hydrology, in steady state well hydraulics, groundwater hydraulics, and also in permeability and seepage in soil mechanics. So this you don't need to memorize. In case you forget, as you see, this derivation is simple. You just have to do one integration. So because if you memorize, you might miss out a 2 or something. So just do it. Then we're left with this last topic in seepages. Yeah, so this is coming to 1D seepage, as we already saw. What is the 1D governing continuity equation? It is suppose we take x flows only along the x direction. It is del Vx by del x equal to 0. And Vx is nothing but minus k del h by del x. So it is minus k del square h by del x square equal to 0. And now if you have boundary conditions that h of x equal to 0 is some h1, h of x equal to L is some h2, we see that the solution to this equation is a linear. So integrate this, you get h of x is nothing but h1 plus H2 minus H1 by L into X. That's all. So when X is equal to, so this is the solution. It's a linear. When X equal to L, you have H equal to H2, and when X equal to 0, you have H equal to H1. This is the solution. Straightforward. Now, if you have two soils in series, for example, if you have two soil stratum, this is some bedrock, and this is the ground level. And in the first case, you consider flow perpendicular to the strata, and in the second case, you consider flow parallel. Suppose you consider groundwater flow that is parallel to the strata. Suppose this has a permeability K1 and this has a permeability K2. How do these? What is the effective permeability? Right? Effective permeability. So that is the question. Let us this has thickness H1 and this has thickness H2, and let us consider some length L. Right. What is constant in the blue case? Let us take this as case 1 in series, and this is soil stratum in parallel. The green is in parallel. Now the blue case, all the water that enters K1 has to enter K2, so the flow rate is constant. What is different? Obviously, the head across this is constant. So when soils are connected in series, the head loss is different. Head loss across each of them is different. So the total head loss across the two soils is nothing but the loss across the first soil plus the loss across the second soil. And the total flow is the same. Q is equal to Q1 equal to Q2. This is one idea. So this is very, very similar to springs in series and springs in parallel, but it is different. So spring relates force and deformation. Darcy's law relates the head loss to flow rate, the hydraulic gradient to flow rate. So the relation, whenever the relationship is linear, you have the special cases of series and parallel. And in the green case, when you have soil stratum in parallel, the head loss is the same. Head loss is same. And the flows are different. So the total flow rate is Q1 plus Q2, whereas the total head loss is the same. Now, so I can go ahead and derive it, but let me do it when we solve a problem. So let us solve this problem. It's a simple problem. So permeability tests were carried. I hope the size is visible, or let me increase it. Permeability tests were carried out in two different layers, and they have these values: the horizontal and vertical permeabilities of the two soils. The relevant horizontal and vertical permeability for each layer is indicated. What is the ratio of the equivalent horizontal and vertical coefficients of permeability? Now, let us solve this problem. So in one case, they are in series. So here it has K vertical 1, K vertical 2. In the other case, the flow is parallel. When flow is horizontal, the flow is parallel to the soil strata. So here it is K horizontal 1, K horizontal 2. So the flow direction is like this, and here the flow direction is like this. Let us write down. Here the flow is constant. So Q is constant. What is Q? Q is nothing but KIA. Let us take this A to be L, and into the plane of paper, let it be just 1 unit. Is K V1. The head loss along the first one is, let us say, this has a thickness of H1 and this has a thickness of H2. So flow length is H1 here, and let the head loss be some delta H, right? So Here the head loss is head loss is delta H1 divided by the flow length H1 into the area, which is L into 1. But it is also equal to KV2 delta H2 by H to L. What is the equivalent permeability? So equivalent permeability is Q by delta H1 plus delta H2. Right? So this is H2. Yeah, so Q by L is the discharge velocity. Delta H1 plus delta H2 by capital H1 plus capital H2 is the net hydraulic gradient. So this will give the net head loss. So this is nothing but the net total head loss. This should be equal to delta H1 plus delta H2. What is delta H1? Delta H1 is, rearrange this equation. You get Q by KV1. Let me check. So let us say the total head loss is delta H, that is equal to delta H1 plus delta H2. What is delta H1 plus delta H2? It is Q by KV1 H1 by L plus Q capital H2 by KV2 L. And what is delta H itself? It is the net head loss, and that is equal to the total flow rate multiplied by the total length of the flow. What is this? It is H1 plus H2 divided by what? The equivalent permeability, which is Kv, and the area of cross section remains the same as the series, as they are connected in series. So this is equal to QH1 by K vertical 1 L plus QH2 by K vertical 2 L. Now rearrange this. So Q gets cancelled on all sides. And then we have, and L gets cancelled as well. So you have 1 by K vertical. The effective vertical permeability is nothing but 1 by H1 plus H2 into H1 by KV1 plus H2 by KV2. So this is nothing but the weighted harmonic mean of individual permeabilities. So the individual permeability is weighted by their flow length, right? So that is the effective vertical permeability is the weighted harmonic mean of individual permeabilities. And similarly, when we have them in parallel, we say the head loss is constant. So to take a section here, this may have h equal to some h. This is a different h. So this, let us say small h1 is the total head, and here the head is small h2. So the flow length is L. This is the flow length, and the area of cross section is h2 and h1 respectively. So here both the soils are subjected to the same loss of head. So delta H is the same, but the flow rates are different. So the total flow is Q1 plus Q2. Now by Darcy's law, it is K H1 into the head loss, which is delta H, by the length of the flow, which is L, that doesn't change, but the area of cross section changes, which is H1 plus K H2 delta H by L H2. But what is this equal to? It is equal to the net flow rate. And let us suppose then the equivalent horizontal permeability is KH. By Darcy's law, it is KH into the net hydraulic gradient into H1 plus H2. What does this say? The equivalent horizontal permeability is KH1 into H1 by H1 plus H2 plus KH2 into H2 by H1 plus H2. Therefore, the net horizontal permeability is the weighted arithmetic mean of the individual horizontal permeability. So this is weighted arithmetic mean weighted by H1 and H2, which are the cross-sectional areas, and this is weighted harmonic mean. Weighted harmonic mean. In this case, now we just have to plug in everything into this formula. So here H1 is equal to 3 meters, H2 is equal to 4 meters, and KH1 is equal to 4.4. Let us 4.4 into 10 power minus 3. KH2 is equal to 6 into 10 power minus 1. And KV1 is equal to 4 into 10 power minus 3. And KV2 is equal to 5.5 into 10 power minus 1. Now let us solve. What is KH? So KH is equal to H1 by H1 plus H2 is 3 by 7 into this value to 4.4 into 10 power minus 3 plus 4 by 7, which is H2 by this thing, into KH2, which is 6 into 10 power minus 1. So can you find out what this value is? It is 3 by 7 to 0. So this turns out to be around 3 into units are meters per second. And similarly, what is kV? Or rather, let us say 1 by kV from this formula. Right? 1 by kV is, again, you have H1 by H1 plus H2, which is 3 by 7 divided by kV1, which is 4 into 10 power minus 3, plus 4 by 7 divided by 5.5 into 10 power minus 1. So let us see what this is. So this is about 108.18, 108.18. So this is 1 by kV, which means kV is equal to inverse of this, right? This is about 9.24 into 10 power minus 3 meters per second. Now, what is asked in the question? So if you see, the question is the ratio of equivalent horizontal to vertical coefficient. So we want KH by KV, which is 3.446 into 10 power minus 1 divided by 9.24 into 10 power minus 3. 3. So this is
37.28, sir.
yeah. So it is 37.28, and the closest answer is option A. So let me if we are option is it's option A. Then let us look at this problem. So this is okay. This is about effective stress. I didn't come to that point, but okay. Then let's look at this problem. So we are given a flow setup shown in the figure. The hydraulic conductivities of the two soils are they are given, right? This is soil 1 and soil 2. As usual, they are given. Assume the unit weight of water as 10 kilonewton per meter cube and ignore the velocity. So there's a numerical answer type, and this also involves some flow. So here the flow is downwards. And what else? Yeah, so there is flow downwards, and at steady state, we are asked to find what is the total head at any point located at the junction between the two samples. So now I said, if you remember, I said that the flow, the head varies linearly uh, when we have 1D flow. So this is a case of one-dimensional flow, and the soil, these two are equal. And if you assume everything is frictionless and so on, you cannot say that the total head at the interface is just half of the head here and head here. It is wrong. What is the reason? The reason is the permeabilities of these two soil are different. So that you should be careful. When within the same, when the soil is homogeneous, the head varies linearly. When we have a difference in the uh, difference in the soil properties, because there is a difference in permeability, it means the slope of the velocity head curve is slightly changing. So you can have head varying like this. It is continuous, the head still has to be continuous, but there can be discontinuities in the slope of the head. So you cannot take the average simply. So that you should be careful. But if you have homogeneous soil, if they are asking some what is the head here, you can just take the average of these two values. Here it is not continuous, so you cannot do that. Anyway, so let us solve this problem. So this is the problem of you assume 1D flow as usual. Assume 1D flow. You assume Darcy's law. And you also assume the pipes are frictionless. So what is the head here? So the head here is, can you answer? Can anybody try that? It is simple, right? What is the total head
4
here?
meters, sir.
4 meters, yes. How does it come? Just use Bernoulli's equation between this point and this point. So there is flow, but flow is very slow. So I can ignore the velocity head. So the total head here should be equal to the total head here. The total head here is only the elevation head. Pressure head is 0. Velocity head is 0. Uh, right. So that is whatever I said right now is wrong. So the pressure head is not 0. The total head here is the sum of, so there is some pressure head here, right? So it is 10 kilopascals. 4 meters is only the velocity head at this point. So if you, sorry, the elevation head at this point is 4 meters. The pressure is 10 kilopascals. So it is 10 into 10 power 3 Newton per meter square. And what is the pressure head? It is P by gamma W. And now you can take, assume that they are given, assume the unit weight of water is 10 kilonewton per meter cube. So it is 10 into 10 power 3 Newton per meter cube. So what is the pressure head? Pressure head is 1 meters. So therefore the total head at this point is 5 meters. So here the total head is 5 meters. And here also, since there is no flow, the total head is 5 meters. Right? So that you need to be careful. Yeah, I also made the mistake, but when you have this 10 kilopascals pressure applied here, when you take the Bernoulli equation between these 2 points, yes, there is a small flow, The total head here is the pressure head plus the elevation head. Elevation head is 4 meters. Pressure head is 10 kilopascals by 10 kilonewton per meter cube, which is 1 meter. So that you should take care. And at the bottom, here you can take. So here, what is the total head? Here the total head is. What is the total head here? Answer?
Sir, -1.
-1. Why do you say that?
Sir, because pressure elevation at is 0, but
Right?
pressure at,
Elevation head is 0 meters. Velocity head is 0. And what about the pressure?
sir, because water is upward flowing.
No. So water is not flowing up. So this you should be careful. Here, pressure has 0 kilopascals. So here pressure head is 0. So here it is 0 kilopascals by 0 kilonewton per meter cube. So pressure head, be careful. Whenever you have a free surface, whether it is open channel flow or a hydrostatic condition or even any pipe flow, whenever you have something exiting to the atmosphere, here you have a free surface. So there you have the pressure head is 0. Here also you have a free surface, but upon that free surface, you are pushing it with some piston of 10 kilopascals pressure. So here the pressure head is non-zero. Here it is you're denoting the free surface, right? So here the pressure head is 0. So understood? That is okay.
Sir, then what will be pressure at just below soil 2?
Just below soil 2. Okay, we will calculate. So what will be the pressure head just below soil 2? Apply Bernoulli equation between this point and this point, right? So here we assume the pipes are frictionless. So here the total head here should be equal to the total head here. The elevation head here is 1 meters. The pressure head here is what it is? -1 meter, right? So this, if you take pressure here as 0, water is as you move above, the pressure drops by minus gamma. Uh, there's a gamma W, right? So from here to here, if you have a hydrostatic pressure distribution, at this point, the pressure has to be 1 into gamma W. But this surface is open to the atmosphere. So therefore, it has to be 0 pressure, which means the pressure here has to be 0 minus 1 into gamma W. So again, pressure head is you divide by gamma W on both sides. So the total head there is 0. Is that okay?
Yes, sir.
Yeah. So the pressure head here is -1. The elevation head here is 1. Therefore, the total head here is 0. So the total head loss across the soil samples is 0. Okay, so that is fine. Now, how do we find the interface? How do we find now is it in series or in parallel? So they are in series, right? Whatever water enters here has to go to this soil. So the soils are connected in series. So Q is equal to constant. Because they are also asking what is the steady state. Did they mention somewhere? Yeah, at steady state. So at steady state means Q is not varying with time. So Q is constant and Q is constant for both the soils because of continuity equation. Now just apply. So they are connected in series. So we can find out the equivalent. How do we find Q? So Q is nothing but the equivalent vertical permeability into the head loss, total head loss into the area of cross section, capital A. So area is not actually required because we'll see why. Let us assume it is capital A. What is the total? Let us find out what is kV. kV is, or rather 1 by kV is, as we saw, it is H1 by H1 plus H2 by kV1 plus H2 by H1 plus H2 by kV2. So in this case, it is simple. This is 1 meter, this is 1 meter. So H1 is 1 meters, H2 is 1 meter. So this is nothing but half. So these two factors are half. And what else is given? They are given it is 10 mm per second and 1 mm per second respectively. So soil one is 10 mm per second. So here you have 10 mm per second, and in the numerator you have a half. Here you have 1 mm per second, and numerator you have a half. So what it is, this will be half into 0.1 plus 1. So this is 1.1 by 2, which is 0.55 second per mm. Right, this is 1 by kV, which means kV is 1 by 0.55. 1 by 0.55. Turns out to be 1.818 mm per second. And always you see this, you can, if you feel if you to check if you're right or wrong, kV will be equal, kV will be closer to the smaller one of the two permeabilities, and kh will be closer to the larger one of the two permeabilities. Even in this problem you can see. So kV is something like 9.24 into 10 power minus 3, which is closer to the smaller one of the two permeabilities, and kh is closer to the larger one of the two permeabilities. So that's a quick check you can do to see if you're on the right track. Now, what is Q? kV into delta H. Delta H is 5 meters, so it is 1.818 into 5. So that is about 9.091 into A. So, and the units, so H is in, so this is mm per second. So, and H is in meters. So let us assume everything in SI units. So we get an into 10 power minus 3 meter cube per second. Assume A is in meter squares. This is the total flow rate. So now we got that. The next step is simple. So the total flow rate we have, and we have, what is the head here? The total head here is 0 meters. The total head here will be 0 plus delta H2, which is also equal to 5 minus delta H1, right? So 0 plus delta H2, which is also equal to 5 minus delta H1, because delta H1 plus delta H2 should be equal to the total head loss, which is 5 meters. Now, what is delta H2? By Darcy's law, again, Q is equal to KV2 into delta H2 by the length of the flow, which is 1 meter, into area. So delta H2 is nothing but Q by A. You can have 1 meter here, and KV2. So what is Q? We just got it as 9.091 into 10 power minus 3, and area into 1 meter. So this is in meter cube per second. Sorry. Yeah, this is in meter square, and this is in meters. Divided by area, which is again in meter square. This is in meter square. Into KV2. So what is KV2? V2 is 1 mm per second. So I have V2 is 1 into 10 power minus 3 mm per second converted to meters per second. So here it is meter cube. Let us check some. So this is fine. This is also fine. Something is not. So this A gets cancelled, and this 10 power minus 3, 10 power minus 3 gets cancelled. So you have, it is just 9.091. So something is off here. Yeah, here you have 1 divided by 1 meter. So that is fine. Okay, Q is fine. So there is a factor of 2 missing somewhere. So this has to be 9.091 into 10 power minus 3. That is okay.
सर इसको ऐसे नहीं कर सकते जैसे अगर डिस्चार्ज इक्वल है तो रेशियो लेके
Okay, you want to say that Q by oh right, I got the mistake, right? You can do that. You can do that, right? You want to say that the discharge is equal. So yeah, but you just need to take care of the correct head. So if you say the discharge is equal on both sides, so you can say it is KV1 into the head loss across the first thing is 5 minus, say the head here is H, right? So in this case, 5 minus H by 1 into the area is equal to KV2 into H minus 0 by 1 into area. So you can do this and get H. You can do that also. Here, the mistake I made is the flow. So here it's not 1 meters, it is 2 meters, right? Because the total length, this is the total flow rate. We are considering the total head loss. So this is 9.818 into 5, which is the total head loss. So Q is equal to KV into the total head loss divided by the total length. So total length is 2, 1 meter for the first soil and 1 meter for second soil. So Q actually is 9.091 divided by 2. So here you have 1 by 2 here. So this is, there's a by 2. So this comes around 9 point, I think 4.51 or so. Yeah, so this is about 4.54 in 4.54 meters. And so you can also check by this. So just take KV to the other side. So you get KV1 by KV2 is equal to, or into 5 minus H is equal to H. So rearrange, you get 1 plus KV1 by KV2 into H is equal to, so is equal to KV1 by KV2 into 5. So V1 by V2, 1 is higher, I guess. Yeah, 1 is 10, 2 is 1. So this is 10, this is 10. So this becomes H is equal to, you get H is equal to 50 by 11. So you can check what it is, 50 by 11. That's also the same, 4.54 meters. So it's the same. So the correct, I think that I have checked the key. The acceptable answers are between 4.50 to 4.6. And we get something exactly in between. So it's the right answer. So the correct answer to this question is 4.54 meters. Yeah, so the approach you suggested is also fine. It's also simpler. The discharge is the same, so you can equate the discharges in the both and then find the head at the interface. Or you can also find out what is the discharge and then substitute in the other equation. But this is shorter because you are eliminating one equation in terms of the unknown Q. So that is fine. So is that okay?
yes sir.
Yeah. Then let us look at this question. So this involves the concept of effective stress. So the idea is you have a soil sample, and Terzaghi gave this analogy between the soils and so in a saturated soil, the interstices between the particles are filled with water. And when we load this sample initially, when you load it by some incremental stress sigma, at time t equal to 0, the entire force will be taken by the, so when we load the sample, this particles will try to come close to each other. They'll try to pack close to each other. In that process, they will pressurize the pore water pressure. They'll pressurize the pore water. So, but as you allow drainage, when you allow the pore water to leave so water is usually incompressible. Water is treated as incompressible in saturated soil mechanics. So instantaneously, the particles will try to come close to each other, but they cannot because the pore water is there. Pore water will take up all the pressure. It is incompressible. It will take up all the pressure and resist the applied force. But as we allow drainage, under the pressure, the pore water will start flowing. Why? Because of Darcy's law. When we apply this delta sigma, the pore water is pressurized, so the pressure head increases, and therefore the total head increases. And away from this region, away from the point of loading, there will be the pressure head is same, right? So water will flow from the pressurized regions to the unpressurized regions. So this that basically you're squeezing water out of the soil under an applied stress. As the water moves out, the the forces between the soil particles will start increasing because water has moved out. The soil particles will start pressing against each other with a greater force, and therefore the force will be transferred by the deformation of soil particles. So that is the idea. So particles will try to slip and take up the interstitial spaces, but you cannot push the water out without applying pressure. So initially the pore water will take all the applied load, and as we allow some time, the applied load will transfer from the pore water to the soil. So this is given by this simplified model. So you have a spring inside a container, and you also have this. You also have the applied force. So when we initially apply the force, if there is no drainage, all the pressure will be taken up by water because of equilibrium, right? Water is incompressible, so the force on either side should be equal. So water will take up all the pressure. But if you allow drainage somehow, under the action of this applied pressure, water will flow out, and at some point, the spring will, as you allow drainage, this piston will move down and it will compress the spring. So at some point, the force K into the delta X, the deformation of the spring will equal to the applied force, and this drainage will stop because you have uh, you have pushed how much ever water you want out. Now the force is taken only by the spring. So this model, so if sigma is the total stress that is applied to the soil, a part of it is taken by the soil skeleton in the form of intergranular forces. So one granule presses against the other, and the other part is taken by the pore pressure U. So this is the this part which is effectively resisted by the soil is the effective stress, and this is the pore pressure. So the effective stress correlates with the soil properties such as void ratio and other things. So therefore, when you apply a total force, at any instant, a part of it is taken by the soil skeleton, which is called the effective stress, and the rest is taken by the pore water pressure. Now, this is the problem we have. A soil sample is underlying water column of height h1, and then the vertical effective stresses at points A, B, and C are sigma A prime, sigma B prime, sigma C prime. And they are given the saturated unit weight of the soil and also the submerged unit weight. So submerged unit weight is nothing but, so if saturated unit weight is equal to the submerged unit weight plus the unit weight of water. That's all. That is simple. Then gamma W is the unit weight of water. Which one of the following expressions correctly represents the sum sigma A dash plus sigma B dash plus sigma C dash? So let us solve this problem. Just remember that the effective stress at any depth is given as the total stress minus the pore water pressure at that depth. Now here, so this is a closed valve, right? This is a closed valve. What does that mean? The closed valve means you don't have any drainage. So you have a closed valve, so no drainage. right? You have no drainage, that is okay. Then what else? Is there any seepage? Is there any flow first of all? No. You have a head here, and here also the head is the same. So you cannot have flow without any seepage. Sorry, you cannot have flow without any head loss. So there is no flow here. So we are under static conditions. So the assumptions are the conditions are you'd have no drainage and you are under hydrostatic conditions or just static conditions. There is no seepage. No seepage. Now, if you are under static conditions, you can determine the pressure of the water from the hydrostatic pressure distribution, right? So let us take the total head, or let us take the pressure head. So what is the pressure head here? So the pressure head here is 0. Here uh, it is just so. So here the pressure head is H1 into gamma W. Here the pressure head is H1 plus H2. So the pressure is H1 plus H2 into gamma W. And here the pressure H is H1, pressure head is H1 plus H2 plus H3. And the total pressure is this multiplied by gamma W. So now we got the total pressures. Now what is the total stress? Let me write that in a different color. So what is the total stress here? You can tell me what is the total stress here? It is what is the weight coming here? So what is the stress? Stress is the force per unit area. Consider a unit area here. What is the force on it? It is the force of the water column, weight of the water column above that, right? So here it is nothing but gamma W into H1. Right? I hope you get it. If you take a unit area here, the force on that unit area is the weight of the water column under hydrostatic conditions. So it is gamma W into H1. Here again, if you take a unit area, what it is, the total stress is the weight of this water column plus the weight of water which is here. So it is the weight of water column H1 plus the weight of water that is there, H2, plus the submerged unit weight of the soil. Why the submerged unit weight? Because under static conditions, these soil particles are immersed in water. So they will displace some amount of water. Therefore, there is an upward buoyant force acting on those soil particles. So if you take the saturated unit weight, you have to saturated unit weight will be the total force, but there is also an upward force on that mass of soil, which is the buoyant force that has to be subtracted. So you take the submerged unit weight. So it is gamma dash into H2. And what is the total stress here? So here the total weight of the water is gamma W into H1 plus H2 into H3. And the saturated unit weight and the weight of the soil, effective weight of the soil. So if the soil is saturated and the water table is not there, then you should use the saturated unit weight. But you have soil submerged under the water, so there's a buoyant force, so you use the submerged unit weight, which is H2 plus H3. Now you can, so you got the total stress and the effect and the pore pressure at every point. The next step is you just compute the effective stress. So sigma 1 prime is what? It is sigma minus u. Both are equal, so it is 0. And sigma 2 prime is what? So here you have gamma W into H1 plus H2, which is u, and gamma prime into H2, right? So it is just gamma prime into H2. And here what it is? Here it is sigma is this, u is this, so this is nothing but u. Again, if you subtract, you get gamma prime into H2 plus H. Here sigma prime H2 plus H3. So the question is asking what is sigma 1 prime plus sigma 2 prime plus sigma 3 prime. So it is, so I have 2 H2 plus H3 into the submerged unit weight of soil. So this is the correct answer, which is option A. This is the correct answer. Okay, so yeah, we are out of time. So let me stop here. And you can ask if there are any questions. Do you have any questions? I'll wait for some time. If you have any questions, you can ask. Yes, Kishore, you said something.
No, sir.
Okay. So what
Thank you.
topics do you? Yeah. You said something. I couldn't.
Thank you, sir.
Oh, okay. So so the plan is we'll do consolidation next time. Problems and consolidation, 1D consolidation of soil. Then shear strength, uh, drained shear strength, undrained shear strength, those topics. Then foundation, shallow foundations. And then yeah, pretty much that is all we can do. So do you have any suggestions? What topics you want? As I said, I'm most comfortable with structural engineering and mathematics. Apart from this soil, that this I prepare and then I come to these sessions. So if you have any, if you want any particular topics, because I think about 4 weeks are left, 4 to 5 weeks for the GATE exam.
Sir, pressure vessels, sir.
Pressure vessels, okay. Like next class we can do pressure vessels. Anything else? Pressure vessels will take maybe 20-30 minutes. Any other topics you want?
Shear center, sir.
Okay, let me note down and yeah, shear center is an interesting topic, right?
Sir, the different part of more circle and shear strength topic.
Oh, okay. Let me. So I think one is pressure vessels, shear center, then more circle, then other topics. Because I will also enjoy teaching this solid mech. I specialize in solid mechanics. My research is in solid mechanics area. So these are some things that I enjoy doing more than geotech and soil mechanics. So yes, we can do these. And problems, yeah, this I can also design some interesting problems from these. In case I'm not able to find any gate, I'll also look for some nice problems so that means those will be like slightly harder than gate so that you can train yourself. If you do those, you can easily do the gate problems. That is fine. Yes.
सर लेसिंग और बीम की प्रॉब्लम्स आती हैं गेट में
Uh,
डीएसएस
can you repeat?
सर लेसिंग एंड बीम्स टाइप प्रॉब्लम फॉर डी फ्रॉम डीएसएस do they
Oh,
come?
design of steel structures. Okay. Built up columns, laced columns.
Yes,
That is
sir.
what you. I have not seen in the last, I think, 5 years. I have not seen those type of questions. But if you want, we can go through that. I have not in the past, and let me see the. We can see the syllabus, right? So we have design of tension and compression members, beam and beam columns, column bases connections, beam column connections. Okay, so that is not mentioned explicitly. Built up columns is what you're asking, right? That is not mentioned explicitly, but we can look at it. That's also a good thing to look at. But mostly, I have not seen questions in GATE. Whenever I look at these papers, I have not seen built up columns. At least in the last 4 or 5 years, it has not been asked. But if you have doubts, we can add that also. Laced columns. I think laced and battened columns, right? Or built up in general. Yes, then I mean you can tell me how many are because we'll finish as much as possible in one session and carry it forward to the next. So can tell me if you have any other. You can also tell me the next session. No problem. You can.
Sir, traffic engineering that PDF will you upload, sir?
Oh, sorry. Yes, yes, yes. I didn't. I uploaded the videos, but I didn't upload it. I'll do it.
Okay, sir. If video is there, and then it's fine, sir. I can go
Okay.
through.
Okay. I'll upload the notes of this by I think it is week 14 or 15. I think week 15 says channel hydraulics. So week 16 probably week 14 then. Uh, yeah, I think this problems. No, not this. Yeah, I think this is the one. Right? You wanted the problems or the notes?
Yes, sir. Sir, both I want, sir.
Oh, okay. I
Because
will
I have
upload.
not.
Yes.
Yes, sir. I have not studied traffic yet in my college, sir. So I want both, sir.
Oh, okay, 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 fine. I will do it. I'll upload both. Because if you have not studied, if it is not yet covered in your thing, I'll write it properly and then I'll upload it. Yeah, I will definitely upload. The video is there. Video with whatever I recorded it, that is there. Maybe you can go through it, but I will also upload the proper notes soon.
Thank you, sir.
Yeah. Okay, so you have suggested me a list of topics. We'll go through them in the next session. So which stage are you in gate preparation? Are you writing gate for the first time or may I know that?
Sir, for first time, I just completed my fifth sem.
Oh, okay, 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 fine. Okay, so fine, we'll do it. Okay, thank you.
Thank you, sir.
Yeah.